Great. Great. Hi. Thanks, everyone. My name is Gabe. My co-presenters will be up shortly, I'm sure. If you attended Hacknights between last summer and this spring, you almost certainly heard me pitch the noise meter project. I'm happy to be up here today with a few people from that team to show you what we built over the past year. We're calling it Track It now, like track the racket. And we've had well over a dozen collaborators over the past year. We're just a few of the people who have been involved. So noise is not just annoying. It turns out it's actually bad for your health. And that's not just about hearing loss. Ingrid from No More Noise Toronto has been pointing this out to Torontonians over the past couple of years. Just because we live in a city doesn't mean that we aren't allowed to experience quiet or get a decent night's sleep. As Ingrid says, pretty much everyone in Toronto has a noise story, and that includes us. We were inspired by Ingrid's work, and we wanted to see if there's something that we could do to help. So we noticed that while the negative impacts of noise over 60 decibels is well established, it's surprisingly difficult to get data about what actual noise levels are, like around us. If you decide to start learning about it, you end up going down this sort of like internet rabbit hole, and you end up looking at these devices that companies sell for hundreds or thousands of dollars that are really awkward to use, that are only really designed for measuring noise levels over the course of a few hours or a few days. What we wanted was to have data that would help us understand the patterns of noise and how those change over time. And so to do that, we needed a way to collect data over years. We couldn't find any devices that would do that in a way that was both cheap and easy to use. And so in sort of Civic tech style, we decided to try to make one. So I've been involved in enough Civic tech projects to know that one of the hardest things to do is to define a scope for the initial release and then stick to it. So we did that by committing to a few simple ideas. The sensor is plugged into power. It's always collecting data. It's sending that data over Wi-Fi to a database online. It's important that it be easy to use, reasonably priced, and we wanted the data to be available publicly, that all the data we collect can be seen by anyone, but also for it to be privacy preserving. So, and like any Civic tech project, it needs to be super easy to maintain. So those were the things that we were kind of aiming for design-wise. So we knew what we wanted to do. At first, we had no idea how to actually do it. We built a couple of mobile apps initially, imagining that we could use old or discarded smartphones as noise meters. That's an idea that we're still open to, but we've since switched to making our own devices, the first ones with parts that we bought online. Things started moving faster when Nick and Clyne joined on. They've got skills in sound engineering, software development, and hardware design. And so they were able to find low-cost components that we could use, designed a custom sensor that we can order in small batches. Clyne will say more about that in a sec. And then Albert designed and printed some 3D prototype enclosures, and we've now since moved on to a pre-made case. I've got some here that I'll pull out in a sec to show you if you want to see what they look like. This is a diagram of how the system works overall. There are these sensors that will listen for noise levels. They'll send that data to an API, gets stored in a database, and then sends to a dashboard, a website, and a sensor manager. I am going to pass it off now to Clyne, who will tell you about the sensor.
I'll do the next one.
Just the arrow.
Hello, everybody. I'm Clyne. I worked on the hardware for the Track It project, and I'm going to go over how we went through the process of designing that to what it is today. To start, we had to make a really simple prototype on what we call a breadboard. When I joined the project, Gabe and Nick had already had some parts selected. And so it's just these two little components that you can order off of Amazon or whatever. Plug them in, plug in a USB cable, and write some code to get something going. we were able to use open source libraries online that did the recording of audio and even did some processing on the recording to get accurate decibel readings. These photos are from Nick, who took it to the sound studio he works at. And he was able to use a very professional sound meter to compare decibel readings against what our prototype here could measure. And he found that we were very accurate within a decibel or two across the whole spread. And with all of that settled, I, having skills about designing circuit boards and all, took this a step further to make it into something that we could order and have manufactured and more easily hand to users instead of a little wired together thing. So these are some photos of the first design we went with. I just made a very simple square circuit board, took the exact parts we had on that prototype and stuck them in. And then that was all with a program called KiCad. That's an open source schematic circuit designing software. After making that design, we went through a manufacturer in China called JLC PCB that for a few dollars can print circuit boards for you, and for not much more, order the components, solder them all so you can have a finished product ready to go. And that's what we did. It ended up costing about $34 per board, which is a bit on the high end for what our device contains. But a lot of that has to do with the scale of the order. If we ordered more of this device and the project took off, the cost would come down. On the low end of cost is the 3D printed case that Albert designed for us. I gave him a 3D model of the circuit board, and he used that to build a case to fit around it. We went to the public libraries here that have 3D printers for just a couple dollars per print, and we also printed some here at U of T, and we had a pretty good, reliable device. From there, we wanted to make a larger order of these sensors. This first one, there's only 5. And while we did that, we also wanted to consider a different enclosure option, something that we could order off the shelf. The 3D printed case, while we can make it fit our device perfectly and it's fairly low cost, going to the library and asking them to print 20 or 50 of these would be a big hassle. The same to do it at the school here. And so we found an off-the-shelf case that we can just order online with the click of a button, few dollars each. I redid the circuit board to fit into the case, and we also adjusted where there's an LED and a button for resetting the device where we wanted those. And we also ordered through somewhere else in China because it was a little cheaper, and that's about that. This design, we have 10 of these boards. A lot of them are running now, not just in our homes, but in a few other people's houses, and it's been working really well. This design will probably carry forward for a larger order as we try to get more noise meters out into the city. And the cost, it was $23 per board, a bit less because we ordered more and all. And then the case too, Gabe actually had to make a little hand jig to drill holes into it, a hole for the microphone and the USB port. And I wish we had a picture. It's very janky. And so we're also looking at getting a company to help us pre-drill those holes so we can have something easier to work with. Finally, this is a little picture of some of the code for the noise meter. It's written in C++ using the Arduino framework, which is a very commonly used framework for hobby electronics. It makes a lot of this stuff very easy, and there's a lot of code online people share for different sensors that all can kind of just plug together. We hosted it on GitHub, so it's open source, and GitHub helped us collaborate on it. There's three of us, me, Gabe, and Nick, contributing code. We can create issues on GitHub to track what needs to be worked on and who can help with things. And a few features of the noise meter. It creates a little Wi-Fi network when you first plug it in to set up the device. It shows this page on your phone. All you have to do is enter your Wi-Fi information and your email, and it'll register itself with our website and start recording noise. We also made sure to have it encrypt the information it stores, like your Wi-Fi credentials. Just as a security measure, we actually met with a cybersecurity expert that advised us on things to do to make sure we have a fairly secure device. The last component to that was putting together wireless updates so that these noise meters can periodically check with our server, see if we've made a new version of the software that might fix things or add new features. And the noise meters can automatically and securely download that so we can maintain the noise meters in the future. That's about it for the device. I think Mitch is next to talk about the database.
Hello, I'm Mitch, and I was responsible for the API database and sensor manager, but like Gabe said, this was a big collaboration with many people. I'm just the guy who ended up implementing it at the end of the day. So the API, or the application programming interface, is the piece of software that sits in the cloud and receives the registration of new sensors when somebody sets it up, and it sends back an email to the person that registered the sensor so that they can then log into the sensor manager, which I'll talk about in a minute. And then the API, most importantly, receives measurements that are made by the sensor every 5 minutes, and then stores those in the database. And the database stores a lot of different information about sensors and the owners of the sensors and so on, but the primary purpose of the database really is to store all the measurements, which, as I said, they come in every 5 minutes from every single sensor, and they store a timestamp of when the measurement first started being taken, device ID or sensor ID, and the minimum, maximum, and mean, which is sort of like an average decibel level. So that's a lot of little bits of information constantly coming into the database through the API. And the sensor manager is maybe the more interesting part. So for device owners, when they do that registration, like I just said, they get back an email with a link so that they can go and log into the sensor manager. And all you need is, thanks to Gabe, an email address. All you need is an email address, and then you can click login, and it'll email you links so that you can log in with that as your password. And then once you're logged in, whether you have one device or 20 devices, you'll see for each of your devices, you'll see a bunch of information, including the latest 24 hours of measurements that it collected, when the last measurement was collected, and most importantly, what the location of the device is, or the sensor is. So when you set up a new device, it doesn't know where that is located. So it's up to you, the sensor owner, to actually pick that location. And it's a little tricky because we want to protect people's privacy. So in order to do that, the idea is that you put a pin into the map in sort of the nearest point of interest or intersection by your home, if it's at your home. And then you create a circle around that point, which we call the privacy radius, that encompasses where the actual sensor is, and maybe then some, depending on how much privacy you want. So the idea is, the sensor lives inside that circle. And then once that's set, you have the option to enable notifications. So if your device or sensor stops sending data, you'll know within 30 minutes, a day, and then a week, it will notify you, and then it will stop nagging you and give up. And then you can also change your email address. But that's pretty much what the sensor manager does. And this was built on a tech stack of web commands. So a little shameless plug there. This is a platform that my company makes that is for projects like this, where you can quickly stand up sort of a cloud database and build web applications. and it's written in PHP, and that's why we use PHP to actually develop the sensor manager and the API. And then on the front end, we use jQuery for just the basic user interface, Plotly for the graphs, and Leaflet for the mapping. And actually 2 plugins with Leaflet that I didn't know about until doing this project that were super useful. One is called Editable, which made it super easy to drop a pin on the map and draw that circle. And another was GeoSearch, so that you can type in an address and we'll bring you to a specific latitude and longitude. And so next up is Daniel for the dashboard.
Thanks, everyone. So I'm very excited to talk about the dashboard component. When we got started with this project, I was really keen to see the data, right? Like we all have these issues with noise in the city. We all hear your cars whizzing by. We all hear parties and constructions and everything. But actually having proof of that, visual proof that this happened to you is a huge thing. So how the dashboard works, it pulls the data through the API from the database, and it can be accessed by the users from the website. So first-time user, they would probably go to the website first, find the map, the system map that we created that's based on the Leaflet app as well, and then through that navigate to individual pages that correspond to the locations where we're collecting this noise data. Right. These separate pages for the devices are also accessible if you just bookmark the link. So if you're a returning user, you can save that and immediately access your data. So I'm sure we're going to pop open the website at some point, or we can pop open the actual live application as well. But this is what the map looks like. You see some active and inactive locations. So active locations are where you have a noise meter registered currently. It might not be sending data for some reason, but it's registered there. And just some useful functionalities. If we have a lot of devices nearby, then they are nicely clustered up. And once you select the device, you click on the map, it pops open a new page. And you see the device or the location profile. Again, you see the map and the bubble that Mitch mentioned. You see the last recorded hourly average and the trend. So currently at this location, the noise level was 62 decibels and it was trending upwards. So it was currently going up. And then you can see the last week's worth of data. You can zoom in. This is the hourly data, I think, that we see there. You can zoom in and then really check out individual events. You can see some pretty high outliers. You can see 100, 110 decibels even there. So, you can take this, you can save the data, you can take a screenshot, you can tweet it at your MP, you can send it to your neighbors, you can go to the construction and tell them that they're not actually, abiding with laws. Like this is, now those super annoying events about noise, they don't just go away. You have some proof that it actually happened and that it impacted you, and then you can act on it. So this was the most exciting thing for me. And then digging into this data is also very exciting. This is something we haven't done at all, but imagine having months of granular, minute by minute, 5-minute granularity data about noise next to your house. We have data about buildings being demolished next to our noise meter. We have data about the gardener being closed and then reopened. It tells this amazing story about what's happening in the city and how much little things make a difference. Like a rainy day versus a dry day makes a huge difference in noise. So I'm very excited about this side as well and getting more people involved and having people look at this data and tell these stories. We never wrote up any stories actually, but I think that's going to be a very exciting aspect. And if you're curious, we have been working on this dashboard with Python mostly. So the web server and the actual visualization and everything is created in Python using the Plotly library and some Leaflet integrations. Everything is on GitHub, so you can actually go and check out the project source code. You can also contribute, which would be great. So the application itself is packaged into a Docker container, if you're curious. And then that is automatically pushed from GitHub to a Heroku server. So if we make a change to the source code and push it to a specific branch, then it gets published and it's live within 2 minutes. So I think it's a nice setup that allows us to quickly iterate, and for anybody to essentially contribute. Perspective. There.
Oh yeah, great, thanks. The website is you can visit it. It's at tracket.info. And I want to shout out specifically to Mir, who helped a lot on the website, as well as the overall like content design and IA. As well as Rel, Isla, and Chantel, who did a ton of work on content design. Current status of the project, where so Tracket is working. It's in testing. We've got, I think, 4 active devices right now. We've got a few others that we're working to get online. We are about to push a new firmware update that's going to improve the usability of the device, of the setup process. The things that we're going to be testing for in this phase are how resilient the sensors and the system is, how easy it is for new users to get them up and running. And we also want to learn from users who, like Daniel mentioned, want to take the data that's been collected by their sensor to try to advocate for enforcement action or policy change. So right now, volunteers and contributors are hosting sensors. If you want to know when the next batch of sensors is going to be available, you can sign up for our mailing list on the website, and we'll send out a note. In terms of what's next, Manas and Mir have been working on a new React-based dashboard. For the next batch of sensors, we want to have the name actually printed on them. Right now they're plain, and so if you've got any ideas on like how to like print or etch on ABS, I'd love to hear it. We're going to be keeping a close eye on everything during the testing phase, including people's experiences of getting the sensors up and running. So if that's something that you'd be interested in helping with, let us know. We need to figure out how we're eventually going to handle ordering and fulfillment for these. That's not super urgent because we're going to be testing for a while, but if you know how to do ordering and fulfillment that's easy and cheap, please, I'd love to hear about that. And then finally, we've applied for a few grants over the past year to do community workshops in neighborhoods that we know are affected by noise, but and so workshops in those communities where we would be able to offer sensors to folks at no cost. We haven't had luck with any of those grant applications yet. We're going to keep working on it. So finally, I just want to say that, like, working on this project, I've been really astonished by the generosity, resourcefulness, and the amazing skills of the folks who've turned up to help. If we had been working on this project commercially and had to pay everyone market rates, this project would have been done faster, but it would have been astonishingly expensive. So I'm very grateful to have had the opportunity to work with such a talented and generous group. We went through that quickly, but we really want to hear questions if you've got them, and we'll do a presenters breakout afterwards as well, if you want to get into it. Thanks a lot.
I have a question.
Go for it.
Oh, yeah. So my name is Michael, and basically I don't know a whole lot about noise, but my intuition tells me that sources of noise that are close to the sensor are going to negatively impact the accuracy of the data. I'm curious to hear something about that. Do you account for that? Is there any sort of difference between distant noise and close noise? Yeah, thank you.
Yeah, I mean, if Ingrid was here, she would have a great answer to this question. I'm not like a noise scientist, but the way the type of meter or the type of like sensor that these are called sound level meters. And so they're essentially just like detecting the decibel level at the location of the sensor. And so absolutely noises that are very close by are going to be detected as louder because they are louder relative to the sensor. And so that's why placement of the sensor is very important, depending on what is the kind of noise reading that you're looking for. So, I think that's definitely a factor. You know, this is as a kind of community project. We don't have any control over the placement of the sensor or anything like that, and so we need to rely on the person whose sensor it is to be placing it correctly and like you know, like doing that part of it.
Thank you very much. Also, if anyone online wants to ask a question, please type in the chat and I'll make it happen.
And Caleb, can I ask you something?
Maybe okay, just in. Kind of possibly relates to the last question because geography kind of helps with that. Is the next version of the dashboard of the data analysis going to have some maps, like to be able to look at it more in a top down overview of the city?
So I imagine you were thinking something like map or some like global visualization. The reason we're not doing that at the moment is because we don't really have good coverage of the city. I imagine a functionality where you can cover your locations, where you see individual locations. But as until we have like relatively even coverage, I think there would be a lot of bias in any type of other visual like map based.
Oh, yay. Okay, so I have like so many questions about how you get a circuit board designed and printed and like made. How do you find someone to produce it? Is it very hard to design? I don't know. I don't know what to ask because I was like, oh my God, you can do that.
Well, maybe, probably. I went to school for electrical engineering for 4 years, so I have that. I do this for work, so I'm not sure I can gauge the beginner friendliness of it. The boards that we use for the prototype are all open hardware, we call it, where you can see their circuits. And a beginner could just like copy and paste those around and piece something together. With simpler circuits, you can kind of just connect things together and hope it'll work. For more advanced things like USB or other communication, you need to like calculate things about those connections. But then as far as ordering the boards, the websites we use like JLC PCB, their audience is beginners. They sell their circuit boards for $2 to get 5 of them. They do assembly for you for a few dollars a part. And so a ton of people will order, and because they get so many beginners interested, that's why they can be so low cost. So if you are really interested in it, it is possible to make something. And yeah.
Any questions online, Michael?
None so far.
Cool.
So I'm interested about the Wi-Fi password thing. So you were saying it been saved in the your database, right? So what if the user, I mean the host Wi-Fi is kind of changed, or the persons who changed, or the password is changed. So how it does the platform having to ability to change, or how it gonna work? I'm interested on that part.
So yeah, like if you set it up with your Wi-Fi network, but then the network changes or the password changes, we planned out a whole little map of what it will do in those scenarios.
Okay.
When it turns on, it looks for the Wi-Fi and tries to connect with the password you gave. After a certain amount of time, it will give up. I think it gives it a while. And then I think from there, it will switch to its access point mode. and will start blinking its LED.
Okay.
So if you're near it or looking at it, you can tell like something's not right.
Yeah.
Reconnect to it and reconfigure it. At any time, if you've changed your Wi-Fi, you can press its button to reset it and then just go through that setup process again. It's
Okay.
very quick. And if there is no, if the Wi-Fi is bad and you're not around to set it back up, it will just shut itself off after like a half hour.
Right.
So we have that
Okay.
sorted out.
Okay.
And just
Yeah.
to clarify, you said database, but the password never, sorry, the Wi-Fi, yeah, the Wi-Fi password never goes to the database. It stays on the device.
Yeah, stays on the device database.
Yeah,
That's what
yeah.
I mean.
Well,
Yeah,
yeah.
yeah, yeah. But it's encrypted, right?
Yeah,
So,
yeah.
yeah.
And then one other quick thing I'd add is if you do change your password on your Wi-Fi device and you don't think about this thing because it's been sitting there for months, it will send you that alert. So you'll get an email alert telling you that it's not receiving sensor data, and it gives you time to do the things that the client talked about, and it actually stores up what it couldn't send until you do reconnect, and then it will send it all. So you won't lose any data.
So technically to open up the access point, so the user can enter the new password. So to that, right? Yeah. So that is what. So through that mail, you are giving the same access point. It's kind of same role. How about the IV generator?
So we've just got a couple of other people with some questions. Yeah. My question is about the locations of deployment of the sensor. So how difficult would it be to deploy the sensor at street level?
If you have power and Wi-Fi at street level, then it would just be a matter of like setting it up and establishing physical security of the device. That's one of the things we're going to be testing. It's intended to be, I believe it can be. I don't know for sure that the ones that we've deployed right now are like the one at Manas's house kind of like went offline during that giant rainstorm last week. Thankfully, all it took to get it back online was rebooting. But those are the kinds of things we'll be keeping an eye out for. But I think that they can be, we intend for them to be. We haven't fully stress tested them on that yet. Same with like cold.
Just to add, as far as putting a device somewhere more remote, you could, with the device as it is now, get like a USB power bank to power up the noise meter. And then for the Wi-Fi network, you could actually use your phone's hotspot to set up the device. Once it's set up, you can go away and the device will build up its measurements over time. And then you can come back to it, turn on your hotspot, and it'll upload all of its data to the database.
But technically, it will not, same location, right? So user initially gives, this is the location and this is, it will affect the dashboard.
But you'll want to keep it in one location. But you can keep it there with a battery. Check in on it.
Michael, I think I saw a question online.
Yes, you're absolutely right. Anson has a question. Go ahead.
Hello. So I have a question, like, how much power does the board draw? I might have missed the information, but I really want to know because you just mentioned about the power, like putting it in a remote or street level location. How long would it last? Like, for example, for a 10,000 mAh lithium battery, how long would it last?
You'd want to do some math. But
yeah, because I noticed you're using ESP32, and I know there's a low power mode, and the Wi-Fi chip and Bluetooth chip also has that low power mode. Just wondering how low it could be and how long it will last.
yeah, so the device as it is now, it is pretty power hungry when it's running Wi-Fi, but when it's just measuring, the power does drop by like a quarter. Its average consumption, I would say, is about like 1/10 of a watt or like 50 milliamps. If that is helpful for you, you might be able to calculate with your battery how long it would last. I have toyed around with designs that could lower our power consumption even further. It would be a dream of mine to see this run off of like a solar panel, so you don't even need a battery to recharge. but we have not got there yet.
Because the other day I heard about a project that runs just under the lake. I think it's at Port Toronto, and then it measures like the temperature and also the water quality where people actually swim. And they said we can just they just put a sensor into the lake bed, and then it kind of runs for a whole year without much maintenance. Just interested.
Yeah, it's definitely interesting. Sensors like temperature would take less power. We have to
Mhm.
record from a microphone continuously and compute the decibels over it, which takes quite a bit of math. And so
I
we
see.
would
I
have
see.
to, it would be possible to use less power, but it would take some time to figure that out.
Thank you.
I can speak to that for 1 second because that's my project. The water temperature sensors are actually they're designed and built as like an encapsulated device, and they don't use Wi-Fi. They use wide range radio called Sigfox, and that requires much less power. So that's one key difference. I'll just leave it there at that. Maybe do another presentation on it sometime.
Yeah, for sure. I mean, we'd be really interested in hearing about technical details and stuff. It's